framework that we call EM algorithm, where when we fix mu and optimize in C, this will be, you can consider this as the expectation step, and then we fix C, optimize in mu, that will be the maximization step. Any question about k-means? No. Then we started to discuss Gaussian mixture models. So here we have n instances, and the we use a generative framework to sample from mixture of Gaussians, and then the generative framework is as follows: that you have P1, P2, Pk probabilities of prior probabilities of Gaussians. With these probabilities, you select one. Say you selected the i's. So the selected class is denoted with this random variable y. If you select I, then in the next step of this generative process, you draw from a Gaussian distribution with mean parameter mu I and covariance sigma I. And you repeat this n times. This is how we draw samples from mixture of Gaussians. Okay, so this is the density of a point x. It's just the sum from 1 to k if we have k Gaussians. So in this case, for example, we have 3 Gaussians. And px, given we are using the i's Gaussian. This is a Gaussian distribution with mean parameter mu I, covariance sigma I, and this is pi I. Okay, we also discussed how the decision boundaries would look like in that case that the Gaussian, the mixture of Gaussians have the same covariance matrix as sigma squared I, and we calculated these log likelihood ratios, and then we realized that those are just linear functions, so they might look something like this. And we even discussed that if you have 3 clusters, then all these decision boundaries meet in one point. Then we started to discuss what can we do if we don't know the parameters mu1, mu2, mu_k. Those are the means of the Gaussians. If you don't know the joint covariance matrix sigma squared times I, and we don't know the pi I, pi to pi k probabilities either. Then we discussed that one thing we can do is we can write up the log or the likelihood function, which would be this quantity, and we can maximize this. We can try to maximize this likelihood function in theta. So the likelihood function, we write it up. This will be product from 1 to n because we assume that the samples are IID, and then this is the probability of x given our parameters theta. We need to maximize this in our parameters theta. Okay, and I think this is where we stopped last time. So here I just write again here that this would be our, so any questions so far? So this is what we discussed last time. Everything is clear, right? No questions? So this would be the maximum likelihood estimation. The theta hat is just the Argmax of this quantity. And let's quickly look at what happens if we replace these pi I quantities with a hard assignment quantity, on which I mean that the probability of yj is I, let it be 1 if I belongs to Cj and 0 otherwise. So here we assume that these are any numbers between 0 and 1, but they sum to 1. So let's see that special case then the probability that instance j belongs to cluster I, that's 1. If indeed this I is the cluster vector j and 0 otherwise. So let's see that what happens then in our likelihood function. So again, I just copied this quantity here. The pi I is again just the probability of instance j belongs to class I. And so my point is what I want to say, that if put this quantity here, and I consider hard class assignment, which means that out of this k quantity, one of them would be 1, the other would be 0. Then in each of these sum, there would be only one quantity that we can keep, the other would be zeros. And then this term would reduce to this quantity here. So this, in this sum, there would be only one quantity that we can keep, that this is 1. When it's 0, this quantity, then these terms cancel out. Okay, but which is that quantity that we keep? It's this is 1 only when I is Cj. So when I is Cj, that's what we keep. And so then the maximum likelihood estimation, where we maximize this quantity in theta, is equivalent to minimize this in mu and C, this quantity. And what's this cost function? That's exactly the k-means cost function, right? So I just wanted to show that in this special case, when you replace these pi's with quantities that can be just ones or zeros here, then you come back to the k-means problem. Yes?
What happened to the 1 over square root of 2 pi sigma squared term?
Oh, good point. So I assume that sigma is known here. Sorry, and
okay.
So
and then
yeah, just don't worry about it. That's a good point. Right, so I just optimize in mu and C this time. Other questions? There was another slide cheating here, but I don't know if I should mention it. Yeah, but first
so if they're not Gaussians, then this kind of association won't work.
That's true. So you can, you will not come to this. You will get something different here if they aren't Gaussians. But say they belong to an exponential family. Okay, you could still write up these things, right? And it turns out for exponential family, you will end up to something like this, but instead of squared Euclidean distance here, you would have a Bregman distance. Bregman distance. So for each exponential family member, there's also a natural distance that belongs to that member. For Gaussian distance, that's the Euclidean distance. For some other members, there would be another distance here. For even more general families, there would be something here, but who knows what it is. Okay, so what's that? So I mentioned you that I did another cheating somewhere. Who can spot that out?
Yeah, isotropic.
Right, so we assume that the sigmas are all known and they are isotropic. So, but that was another point. Okay, so let me show you. So this is pi I. It doesn't depend on j. This quantity depends on j. Right, so I'm saying pi, probability of pi I j is I, this one if I is j. So, but then
you assume that they are IID in that sense, or in a generative process you assume there's
So the IIDness is independent from these pi's. It's just my saying that here you can see that probability so probability of yj is I. It should be 1 if I belongs to say j, right? But for an other, if I just change j here, I will not get the same quantity, right? So with mixture of Gaussians, if I change j from j1 to 2, this probability will be the same, right? It's pi I. Probability of y1 is I, is pi I. Probability of y2 is I, is y2. But here, if I change probability of y1 is I, is, you know, that depends on j this one.
I was thinking the generative process you described earlier, so you had the xi, yi pairs,
Yes.
they are generated ii according to these two stages. You pick first a sentence with
Sure.
ii, which is going to be the same for all,
Right.
typically for a typical sentence. Once you pick this sentence, then cluster, then you pick the new i's. Or the xi's according to the corresponding time.
Right, so that's what we do in mixture of Gaussians.
Right, but that also follows the same generative process. You follow that.
So here there's no such so in k-means there's no such generative process. It's just you minimize the cost function. I just wanted to show that this is like how you can come from one to the other. But that's it. Okay, so this is just NPV relationship between k-means and mixture of Gaussians.
Is there a more rigorous way?
So you could do, but it would it would make notation slightly more complicated, and I don't really think that we need that. It's just I just think that it's enough to see that in one extreme case, mixture of Gaussian behaves almost like k-means, but. All right. So this is a general mixture of Gaussian or Gaussian mixture model. So sometimes in literature you will see this that Gaussian mixture model. Sometimes you say mixture of Gaussians. They are the same. Okay. So on general, I mean that now the covariance matrix sigma it can be anything. But it has to be positive semi-definite, of course. Okay, but now the covariance matrices can look like this. So any kind of ellipsoid is fine. And then the model is the same. First you choose a Gaussian component with probability pi I, and then you generate a Gaussian, where now the Gaussian can have mean vector mu I and covariance sigma I. Okay, for a second, assume again that all these parameters are known now, but sigmas can be general as we discussed, and let's see how the decision boundaries look now between the different clusters. So we do the same thing that we did before. We calculate the log likelihood ratios of these quantities. What's the probability of the point x belongs to cluster I? We divide this with what's the probability that point x belongs to cluster J. So we calculate these log likelihood ratios exactly the same way how we did before. And then the difference would be that previously these quadratic terms cancel each out. That's why we got a linear decision boundary. But now if you look at that, it will be a quadratic term, right? So if this log cancels the x quantity here, and then in x you will have a quadratic function minus another quadratic function, but sigma I inverse and sigma j inverse they might be different, and because of that, between cluster I and cluster j you can have a quadratic decision boundary. Does it make sense? So your decision boundaries might look like this. If you are in this region, then the points belong to cluster mu3. If you are here, the points belong to cluster mu1, they're cluster mu2. Yes?
What happens to those, like 1 over square root of 2 pi?
Right, so they don't depend on x. So that those come here to this constant. Other questions? And same way as we did before, you can prove that these quadratic functions, they have one intersection if you have mu1, mu2, mu3, if you have 3 clusters. Okay, so now the hard case. What if we don't even know these parameters? Mu1, mu2, mu_k, sigmas, pi's, then what can we do? And then the maximum likelihood estimation will look like this. So this is the likelihood function. We want to maximize this in theta, where theta, they are all these parameters. Okay, so we just need to maximize this likelihood function in thetas, which is so in all these pi's, sigmas, and mu's. So the issue is, so how can we do that? So one is that we calculate the derivatives with all the parameters, and we solve when that system is there. Right? We calculate, for example, if I want to find mu I calculate this with respect to mu I, and try to solve this when it's there. Yes?
What is the notation means over there? That those two conditionals.
This one?
Yeah.
Oh, that means that there's a typo there. Good question. So what I meant to say is that probability yj given I given theta times probability of xj given yj and theta. So theta is just a parameter.
Does that in general have a closed form solution?
No closed form solution, right? So that's an issue. Yeah.
The norm you have there on sigma I is the two norm. So you have 2 pi norm sigma I.
Oh, here.
Yeah.
That's the determinant.
But that,
Yeah, so this wasn't really a unique solution because you kind of got these permutations of all your clusters.
Right, that's another issue there. So we have some issues. But at least we know that we want to maximize this function. And if we could solve these kind of equations, at least we know that those points would be, hopefully local maximum points. If you are not local, maybe they are local minimums. But that's least something there. Another thing we could do, right, so this is nonlinear, non-analytically solvable. That you don't solve this, but you just move towards the direction of the gradient with some appropriately chosen step size.
you mean gradient ascent?
Yes.
Why this? And you said descent, but you want to maximize, right?
Oh, sure. On the
Ascent.
descent on the.
What you're gonna add,
Good point. Intentionally, I put some typos here.
Put a negative sign in front of it and then do
Yeah. Right. Right, so we could use the gradient, and we just need to choose the step size. And we will have some other issues that we want all these pi's to be non-negative, sum to 1. That might be a bit difficult to force with gradient ascent. These sigmas has to be positive semi-definite.
Can you start with any point in the simplex and just do like some tranquil on the simplex?
So
for
you
pi's?
can for pi's, but we have other variables too.
Yeah, okay, but you first do mu and then you do pi.
Right. So So your solution is you want to fix say mu and sigma, and
Yeah,
then
pi and then
pi on the simplex.
any grade, I don't know.
Sure. So you might try to do that. What would we do with sigmas?
Well, there is this, I just know the name, positive definite cone, you
Sure.
can step over that.
Right. So we have to optimize things in a positive semi-definite cone. How to do that? Other than downloading a cone programming toolbox.
Can't you, maybe you can just pick up a rotation matrix and multiply on both sides of the covariance matrix.
That's still just like a convex set, and then you use the Frobenius norm instead of the usual norm. You go in there. You can do still like gradient center. You could. I mean, I don't know how complicated it is, but it's just a convex set in a different space.
But how does that have? So it's true, we have a convex set.
And you have the trace as the inner product.
But so the issue is, so we are in a convex set, and I have a gradient. I have to make sure that I don't leave.
Yeah, but the spectraplex is generated by U transpose, where U is, you just want to stay in the semi-definitive, right?
So sigma is a matrix,
Yeah.
and I want to make sure that. So I start from a sigma, positive semi-definite things, and I update to another positive semi-definite. So I want to update to another matrix, which points towards the gradient, and that's has to be positive semi-definite too.
Yeah. So you know that symmetric matrices are generated by U transpose for U in
Mhm.
R2. So you just look at the U that maximizes the product of the trace from the whatever the gradient is, and just go in that direction.
Right. So so that's one solution. That sigma is positive semi-definite, right? So I know that sigma can be written as U transpose.
Or even you can just write it as the spectral of this composition. It's going to be the sum of lambda I, UI transpose, where UI is the eigenvector. That's easier.
So you want to say some lambda I and
Lambda
UI?
UI transpose, where UI is just the vector in R.
Sure. You can do it. So why I wrote here, because now I just have, so my point is, in this case, I just need to optimize this in U, and then the sigma solution would be U transpose. You can do this way as well, but now you would have one more parameter as lambdas. Doesn't matter, so they are kind of equivalent. But indeed, that's one way that if you ever have a cost function where you want to optimize that cost function in positive semi-definite matrix, then sometimes this might help if you just write that positive semi-definite as U transpose, and then you optimize in U. The issue is that sometimes it can make, so now you optimize in U, you have a U, then sigma will be U transpose, that's your solution. Sometimes if you do this, then this cost function might become very ugly, in that sense that there might be lots of local optimum points. So it's not always good, but sometimes it's okay. Yes?
How about just directly optimize sigma by use projected gradient set?
So that's another solution, that you can optimize sigma directly. You forget that it was positive semi-definite matrix, and then you got a solution, and you project that solution to the cones of PSD, positive semi-definite matrices. Sometimes that works. Yeah.
In practice, what do you actually do usually?
None of these. EM. And I just want to discuss with you that, so in this case we can use EM, but sometimes you have a cost function where you cannot do. And then you decide what works. Okay, but I want to discuss that if you see a cost function like this, then what would we do? Okay. And so the other thing I wanted to mention, so we discussed possible ways, but I hope you also see that none of them is that trivial, actually, right? Yep.
So when you say global body often is too slow, but computation is really easy. So if you
Convergence is slow.
yes, but
yeah.
so how do you weigh things when you're actually coding between using gradient descent or Newtons?
So we will. So let's ask this question. So gradient and Newton.
Because Newton computation is really ugly, but it's really fast.
Right.
It's going to converge like super linearly.
Mm-hmm.
How do you choose which of both you use?
So it depends really on you. That if you have the patience to implement Newton, then right. So I would also always. Okay. So there are more complicated things. So it's not just computation. So if you have patience to implement Newton, I would always do Newton. But another problem with Newton that if the dimension is big.
Yeah, computing the inverses or
Right. So in Newton you have to invert sometimes a big matrix. That's not always good. Alright, so our solution for this now will be to try to solve that with the so-called expectation maximization algorithm. Okay, so EM is a general algorithm where so like a framework where it's designed to do maximum likelihood estimation in case where in your model there's some hidden parameter. So in our case, the hidden parameter, hidden random variable, I would say, it was the cluster labels. We will see that in this case, in mixture of Gaussians and in some other models, for example, in hidden Markov models, EM will be again like a gradient descent, but it finds the step size in such a way that all your constraints will hold. Okay, so we will prove that in each step you increase the likelihood function, just as you would do in a maximum likelihood estimation problem. But all of the constraints that those pi's has to be non-negative, sum to 1 that will hold, the sigma will be positive, semi-definite matrix and so on. So you don't need to bother with choosing the right step size. It will just happen. The EM algorithm will have two steps. One is the E step, where, as we discussed, you will use EM when there are some hidden variables. And in the E step, you replace those hidden variables with some expected values. And after that, you do a maximization step, which will be just like a standard maximum likelihood step after completing the hidden data. So we will see that in more detail, and then it will be clear. So, for example, for mixture of Gaussian case, this is our model. I have two, but only one. Right, so this is our data. We have x1, x2, xn points. And we have some unknown variables. In case of clustering, these were by1, by2, by they are the cluster labels. So for example, by1 is 2, it means that x1 belongs to cluster 2. And in mixture of Gaussians, we have parameters data that we want to estimate. Those are all these mean vectors, the probabilities, and the sigma covariance indices. And our goal is to do a maximum likelihood estimation, that is to maximize this log likelihood in data. Okay, so this is the setup. And we have similar setup, for example, in hidden Markov models. Who doesn't know what hidden Markov models are? Who knows what hidden Markov models are? Alright. So for those who don't, in this case, you again have some random variables, x1, x2, x3, x4, and so on. These ones that you observe, that's your observation, x1, x2, x3, x1. And you assume that how they are generated, they are not IID like we have in mixture Gaussian model, but there is a hidden Markov model, which is denoted by by1, by2, by3, by4. So you can think of that by1 is, say, it can be a discrete number like 1, 2, 3, 4, and then depending on what state you are, you go to a next state according to a Markov transition, and then you can go to another state according to a Markov transition, but you can never directly observe the states of this Markov model. You can just have some noisy observation depending on the state. You observe x1 in state y1, x2 in state y2, and so on. And your goal is that having these observations, you want to estimate these unknown random variables y's and all the parameters of in this hidden Markov model, such as what's the transition probability of going from state I to state j, or what's the probability of observing xt in a state I. We will have a whole lecture on this later. I just wanted to point out that this model also fits this assumption that we have some hidden random variables in this case as well that we want to estimate. But let's go back to the mixture of Gaussian case. So this is our goal. We want to maximize this log likelihood function. And so now we will do some tricks, so you have to pay attention. So we will introduce arbitrary distribution Q. Okay, so this was the log likelihood. We want to maximize this in theta. And if I just try this Q distribution here, then nothing changed because I integrate it out. So what will happen now, I will do a few tricks that first will make no sense. But at the end, hopefully, you will see why we do those things. Okay, so just be patient for a while and ask questions if something is not clear. So the point is that I introduce this distribution Q, and then this log likelihood is the same. And then I can write P, our data given the parameters theta t, that this is P by given P by and the data given theta divided by and theta. Alright? Let's clear this step, right? If you get lost, just raise your hand. So we use this identity, it's just the base rule, and replace p theta here, and then I got this equation. And then, right here, the position. Yep.
So you were maximizing the perspective theta.
Theta, yeah.
Then what is theta t?
Right, so I maximize, this is our goal, and I will do that through an iteration. And let's assume that at iteration t, in my estimate, my maximized parameter is theta t. Okay, so in next iteration, I want to get a theta t plus 1, which is even better. Okay, good point. All right, so can everyone see what I write here? to log probability if all my data given theta t. So what we do here, this is what we is integral for an arbitrary q by log p by theta t divided by p y theta and theta t.
Sorry.
Yep.
Q is just a distribution.
Any kind of distribution.
And Y doesn't depend on anything. Y is just a mute variable.
So I'm just saying that for any kind of Q distribution, these equations hold. That's my. And I will tell you why we need that. I just want to introduce a couple of equations that we will need one step later.
But then Y has nothing to do with D or theta, otherwise.
So, so we will come back to that. What I want you to see now, that for any distribution Q, any kind in the universe, these are identities that would hold.
Not if the function inside depends on Y. Right? Log P of D given theta, if that depends on Y, then that's
So,
the expected value.
So, okay, so let's come back to this first equation. I'm claiming that for any distribution Q, this holds. No?
If the log of P D given theta depends on Y, that's the expected value.
Oh, D in our case
Yeah, that does.
is x1, x2, xm.
Oh, okay. Then you
Good?
Then.
xm. Alright. And now let's see what this is. So this holds for any Q distribution. This is Qy log theta t minus okay, so here I have minus integral q log q, but then I also add here q log q, so they cancel each out. Plus integral d divided by d. So, right, so my claim is that this holds for any Q distribution. And what's this expression here?
That's a Kullback-Leibniz divergence.
So there's a quantitative term Kullback-Leibniz divergence. It's like a distance between two distributions. So this is the Kullback-Leibniz divergence between distribution Q and Py given data and theta t. This is always non-negative. That's what we know about it, and that's what we will use. What is this expression here?
Entropy.
And this is the entropy of distribution Q. All right. And for historical reasons, this quantity here is called free energy. Okay, we will just, it's not important for us why it's called free energy, but I will just use this name, free energy. It's coming from physics. Okay, so this free energy, and now you have to pay attention. This free energy F depends on theta t, the distribution Q, I denote this by this, and the data D. Okay, so what we had is that the log likelihood is just the free energy plus the Kullback-Leibler divergence.
Sorry.
Yep.
Why it doesn't depend on y?
This one? Because you
Oh,
take,
from the free energy doesn't depend on y.
okay, so for example, the entropy that doesn't depend on value,
Okay,
right?
okay.
Because you integrate it out.
Yeah.
And here, you do the same thing,
Okay.
you integrate out. Alright. And now, the E step of the EM algorithm is that we create a function Q which will depend on the parameter in the previous iteration, theta t minus 1, and the parameter on the next iteration, theta t. And it's nothing else, just the expected value of the log of the joint distribution of y and our data, given the parameter theta, and given the data and the parameter times the t minus 1. Okay, so in other words, you have this log joint distribution, and you take the expectation, the expectation of this with respect to y, and the distribution of that y is just that posterior distribution that depends on the data and the parameter times the t minus 1. So formally, this is just this. So it's integral of the log joint distribution y and data given theta t with respect to this density py given the data and parameter times the t minus 1. Okay, so that's called E step, and you should see why it's expectation step, because you take the expectation of this quantity, where y is a random variable, and for y you will use this posterior distribution. Okay, so Q theta t minus 1 is just integral dy, the probability of y given data and parameter at times that t minus 1 times log the joint distribution in y times the t. Okay, so this is just definition, and you should see that this Q function depends on theta t and theta t minus 1. Theta t minus 1, theta t. Yes?
Is this Q a probability?
Q, oh, this, no, it's just a function between qt and qt minus 1.
What do you put the condition on in between? What's that? Between theta and theta minus 1?
Oh, it's just, it has two parameters, so I could denote it with this though if you want. So it's a function with two arguments.
So,
This is a function with two arguments. The arguments are theta t and theta t minus 1, and it's defined by x.
so it seems that only to term inside the free energy, which is, and free energy minus y, the entropy only, this only contribute, is this term the only contributor?
So this Q function will be this quantity when you replace this Q with this distribution. That's your question.
So that means the entropy and as well as the third term doesn't really matter that much.
Not yet. So my point, there are two things here at this point. That the log likelihood is just the free energy plus the Kullback-Leibler divergence for any kind of Q function. That was one thing. The other thing that's important that I introduce this function Q. That's all, okay, for now. And the M step will be that we maximize this Q function in theta here, in the first argument. So this Q function has two arguments, theta t minus 1. We maximize, the new theta t will be, we maximize this Q function in the first argument, that's theta t. And we will do this iteration that you have theta t minus 1 parameter, you maximize the Q function in theta, that will be your new theta t. You put that theta t here, you maximize Q again in the first argument, that will be theta t plus 1, and so on.
So in previous slide you said that this field is like taking hidden values using inference, but we are actually like taking an average or possible values that they hidden.
Right, so that's what, so yes, we take the average, yes, yeah, that, exactly.
Or do you have also in mind like actually taking a sample and then plugging in?
No, we just take the average. Yep. Okay, so this is the EM algorithm. At this point, it shouldn't make sense why it's good, but the algorithm, I hope that the steps of the algorithm are clear. That we create a Q function like this. It has two arguments, theta t minus 1. In the F step, we maximize in the first argument, that will be theta t. Next iteration, we replace theta t minus 1 with theta t, maximize again in the first argument, and so on. And my claim is, if we do this iteration, then this log likelihood is not decreasing. It's either going it either remains the same or it increases. So that's why we say that it's like a maximum likelihood estimation, in that sense that it increases the likelihood function, or at least it doesn't increase. Alright, so E step, M step is clear? Yes?
I understand the N step, but what's updating in the E step? So you have your...
In the E step, it's just you calculate this expected,
you just calculate.
Or you just define this Q function, that's the E step. And it's called E because of this expectation here. In some special cases, we will see that actually you can update this distribution, that in practice it will mean. Okay, but in theory, the E step is just you calculate this expectation, the M step you maximize this Q function. Yes?
So the E step, I don't see the point of using theta t rather than theta, because you're just calculating the function over any given theta.
Sure.
Right?
So it can be theta. It doesn't. It's just notation, if you will.
Okay.
Okay. Yes.
What's the intuition, I
We
guess,
will-
for physics?
Oh,
Like,
let's not go there because it would take like 20 minutes at least to cover that. So I don't want to explain what's the intuition between free energy and entropy, but just save some time. Okay. So, and we will not need that. We just need this definition. But I can give you pointers if you want to. Okay, so, but we have more important things to discuss, namely why this makes sense. Okay, so this is what we know. This is the log likelihood, this is just the free energy, and plus the Kullbacher-Leibler divergence. In the E step, we define this Q function. So now I use, so we just have theta and theta. That's the E step. Observation 1, if I choose this Q function, Q distribution, to be this, the posterior of y given the data and theta t, then this Kullbacher-Leibler divergence here will be 0. So that's one property of the Kullbacher-Leibler divergence. The Kullbacher-Leibler divergence between distribution P and distribution P, that's 0. Okay, that was easy. And then what we have is that the log likelihood, if we choose this Q function, that Q is this function, so this Q function now is this posterior, this Kullback-Leibler divergence is 0. So the log likelihood is just the free energy if you choose this Q function in the right way. Namely this. Alright. And then let's use the definition of the free energy. So the log likelihood is just the free energy if I choose the Q function to be this posterior distribution y theta theta t. We have the theta. Okay, so the free energy is just integral Q log p by d. So integral, this is the Q log p by d, minus the entropy of Q, and this was our Q. So this is just the definition of the free energy, this line, where I substitute this Py given data T to T into the definition of Q. Okay, so what we do, so this is the E step, and what we do in the M step, we maximize the Q function in theta. Okay? What was the Q function? The Q function is defined here. We maximize this in theta here. Because of that, we know if we maximize this here in theta, and that's denoted with theta t plus 1, then because of that, this expression is less than this when I write theta t plus 1 here. Okay, so I maximize this. This is the Q function if there's theta here, and then maximize that. So it will be theta t plus 1 here, and I don't change these guys. Alright, so once again, this is the log likelihood. We discussed that the log likelihood is just this expression. If you choose Q function to be this, the Q distribution to be this. And then in the M step, what you do, that you maximize this expression here in theta. So if I maximize this expression in theta, it means that, and that will be theta t plus 1, right? The argument where this is maximized in theta, that's theta t plus 1. So if I write theta t plus 1 here, then this expression is bigger than this. Who got lost? No one? Someone? Right. So this was clear up to this point, right? That the log likelihood is just this expression. And if I maximize this Q in theta, where I got the maximum, that will be theta t plus 1. Okay, so let me write it here. Theta t plus 1, theta t plus 1 is arg max Q theta theta t. From this it follows that that this expression is less than this. All right? So what we have, that the log likelihood with parameter theta t is less than this expression. Okay, using this, we will prove our main theorem that if if you do the CM iteration, then the likelihood function is not decreasing. Either increases or remains the same. We already discussed the log likelihood is just the free energy when you use Q function, choose Q distribution to be this posterior distribution. And we already discussed that in the previous slide, that this log likelihood is smaller or equal than this expression. So that was the last line in the previous slide. Right? This log likelihood is not bigger than this expression. Alright, so the log likelihood is not bigger than this expression. And now we use again the definition of the free energy. That if you look at this definition, the free energy is integral Q log joint distribution between y and theta minus the entropy of Q. Then if I choose Q to be this distribution y given the and theta, then this is just the free energy where instead of theta t, we have theta t plus 1 now. So it's just, you look at this, that's the definition of the free energy. If I put theta t plus 1 here, and the Q function is just p y given theta and theta t, then we come back to this. Okay, so this is by just the definition of free energy.
Question.
Yes?
When we have the entropy, right, entropy only depends on Q, but in this case, in our case, Q actually depends on theta t, right?
Yes, but not theta t plus 1.
So we can actually move from theta t to theta t plus 1.
Mm-hmm. Right, so, oops. So the free energy depends on Q, theta t, and the data. This is depends on Q like this, and depends on theta t like here. So in here, this case we have theta, instead of theta t, we have theta t plus 1. And the Q distribution is just this. In the Q there's theta t, but there's no theta t plus 1. Okay? And what we proved then so far, that the log likelihood is less than the free energy, where the free energy has parameter theta t plus 1, and the Q distribution that depends on theta t and the data. And we are almost done, because now we know again what's the definition of free energy. The free energy is just the log likelihood minus the Kullback-Leibler divergence. Again, log likelihood is free energy plus Kullback-Leibler divergence. So free energy is log likelihood minus Kullback-Leibler divergence. So this free energy is the log likelihood of the probability of the data given theta t plus 1 minus the Kullback-Leibler divergence between this distribution and theta y given theta t plus 1. And why are we done?
The explanation is strictly positive.
Yeah, because this is always non-negative. And then we prove that this guy is never bigger than this. Okay, so it's lots of calculations, and it makes sense only at the end. But yes?
I'm just going to ask, what is this magic and how did you get to this?
Right, so let me come to that. But if you check the proof step by step, then hopefully you can put the pieces together. If not, then ask me. Okay, so what's the magic? So what happens here actually? Next slide, but first, so this is what we do. Our goal was to find the maximum of the log likelihood in theta. What we do, we introduce in the E step a Q function, which is defined by this quantity. And in the F step, we maximize this Q function in theta. And you do this iteration. Create a Q function maximizing theta, and the new theta comes here in the second argument, maximize again in the third argument. And if you do this, then the statement is that the likelihood function is never decreasing. Okay, so this is the magic what happens. That we proved that the likelihood function is always a free energy plus a Kullback-Leibler divergence. So the likelihood function is always bigger or the same as the free energy. Okay? The likelihood function has parameter theta t, the free energy has parameter theta t. So this is like a picture. This is a likelihood function, and under that likelihood function there's a free energy curve, because the likelihood function is free energy plus Kullback-Leibler divergence, and the Kullback-Leibler divergence is non-negative. And if we choose a right Q function in the free energy, we also check that the Kullback-Leibler divergence disappears. So the free energy will touch the likelihood function from below, right? And then you maximize that free energy function. So for example, this is black curve is the likelihood function. The free energy is below that. If we choose the Q function right, then the free energy will touch this likelihood function, for example here. And then we maximize the free energy in theta, and that will be theta t plus 1. We come here. And we again we calculate a new free energy that will touch the likelihood function from below, and you do this iteration. Does it make sense? So the free energy is always below the likelihood function. But if you choose the Q function right in the free energy, then that free energy will touch the likelihood function. And that's why if you optimize the free energy, still somehow it will optimize the likelihood function. Did it help? Good. Okay, it's very important what the starting point is. So for example, this is the likelihood function again. If you start your iteration here, the EM, then you might converge there. If you start your iteration here, then you might converge there. So it's a local optimization method. Yes?
And you know that T's do converge. If they converge, then yeah, then the maximum likelihood does converge to the local maximum. How do you know that that does itself converge?
So the what we proved that the likelihood function never decreases. And you arrive from this, it doesn't follow that those thetas will converge, they might just go into a cycle. And you can prove that under some conditions, indeed they would converge, but we didn't do that.
Is it very hard? What are the conditions on P, for example? So if it's like from the exponential family or something like that, you see they're going to converge?
Yes, so we will see those equations. But generally it's not that trivial, right? Yes.
I don't understand why it might not converge, because you have the likelihood bounded and you have the increase.
Right. Imagine that the likelihood keeps the same. But you go from one parameter, same likelihood.
Yeah, but I'm still at maximum like.
Right, but the parameter wouldn't converge. The function value that converges.
Yeah.
Yes.
Yeah. So it doesn't matter. You can pick one.
Sure.
But the parameter doesn't converge. You don't know you're going to converge to a local max.
It's a local max. Right?
So,
but not to a local
right.
max.
So one thing, we didn't prove that we would converge to a local optimum point. We just proved that using this iteration, the likelihood function wouldn't decrease.
Yeah, but
in theory, you might even get stuck here.
Put the previous slide. Can you put the previous slide? There you go.
Oops.
No,
This one?
Yeah, it says converges to a local max, but that just happens if theta converges.
Right. So this is you can prove this one as well. We didn't prove it. All we proved that the likelihood function is not decreasing, and usually it increases. Okay. Okay. There's one more generalization of this EM framework, and that's called variational methods. So what we need for this EM method, you have to calculate an optimal Q function, Q distribution, right? And if you choose, come back here. So in the EM algorithm, you choose the Q distribution this Q distribution to be Py given the data and parameter theta there. Sometimes this distribution can be very ugly, and we cannot just choose it. But what you can do, at least, we prove that the log likelihood is always bigger or the same as the free energy for any Q function. So at least what you could do, instead of choosing the optimal Q function, you can just choose something that's not too bad. So in practice, what we did, that we had this function, free energy, we maximized this in Q, then in theta, then in Q, then in theta. But we were always in the EM, we were always able to calculate what's that Q function that gives us the global maximum when the Kullback-Leibler divergence is 0. But instead, if this Q function is very ugly, you could just choose a suboptimal Q function where the Kullback-Leibler divergence won't be 0. But still, you can optimize in Q and then in theta, then Q in theta. It's just you never find a global optimum. Yeah.
Sorry, isn't the KL divergence always?
So in the EM case, we choose a Q function such a way that the Kullback-Leibler divergence became 0.
Right. I mean, it's always not negative. Right? So how would log P be greater than free energy?
This one?
Yeah.
So this is the free energy plus a non-negative term.
Sorry. Yeah. Okay. Yeah. I don't know that.
Okay. So, so what you do is that instead of a full E-step that we did in the EM algorithm, you just do a partial E-step, which means that you try to solve this, maximize this free energy in Q, but you might not find a global optimum where the Kullback-Leibler divergence would be 0. Or in other ways, you try to minimize this Kullback-Leibler divergence in Q, but you might not be able to set this Q function exactly to this distribution. And the M step is the same. You try to maximize your free energy in theta. So the want to find the. I was looking for a picture, and I remember I had, but I can draw a picture. Let me come back to this slide. Okay, so this is what happened in the EM algorithm, right? That we always find a Q distribution such that the F function touched the log likelihood function. With variational methods, you just find the F function that will be below this, but you try to optimize. So you try to optimize this F function still in Q in such a way that it should be as close to the likelihood function as possible. But sometimes, again, you cannot use that Q function that would minimize the Kullback-Leibler, that would set the Kullback-Leibler divergence to 0, because sometimes those distributions are so complicated. Alright, so any question about this? So what we saw today is that if you do the EM algorithm, then the likelihood function won't decrease. And my time is over, so next time what we will do is that we will quickly see how to do these calculations for the mixture Gaussian model, and then we will continue with principal component analysis. So there were lots of calculations, but I hope if you check the details, then everything will be clear. If you have questions, then please ask me.